Up next, secrets of the James Webb Space Telescope has made some remarkable discoveries, and the latest findings may have significant implications for our understanding of the universe. The telescope has discovered galaxies at the far side of the known universe that are much larger and more mature than what our current model of the Big Bang predicts. This discovery raises questions about the fundamental assumptions we have made about the universe's origins and its evolution. The standard model of the Big Bang suggests that the universe began with a massive explosion, followed by a rapid expansion that lasted only a fraction of a second. This explosion created the building blocks of matter, which then cooled and began to form stars and galaxies. However, the discovery of these mature and massive galaxies challenges this model, as it suggests that they formed much earlier than we thought possible. One possible explanation for this discovery is that we are observing galaxies from another universe colliding with ours. According to the multiverse theory, there may be many other universes beyond our own, each with its own set of physical laws and constants. If our universe is just one of many, then it's possible that some of these other universes are colliding with ours, creating new galaxies in the process. While the multiverse theory remains controversial among scientists, it is one possible explanation for these recent findings. However, other theories also offer potential explanations. For example, some researchers have proposed that the early universe may have undergone a period of rapid expansion, known as cosmic inflation. This expansion would have caused regions of the universe to expand faster than others, leading to the formation of large and mature galaxies. Regardless of which theory proves correct, these latest findings have significant implications for our understanding of the universe. If we are observing galaxies from another universe colliding with ours, it could have profound implications for our understanding of the nature of the multiverse and the possibility of other universes beyond our own. Furthermore, if the multiverse theory is correct, it raises questions about the nature of reality itself. If there are multiple universes beyond our own, then what is the true nature of the universe? Is it a single entity, or is it made up of many different universes, each with its own set of physical laws and constants? If these galaxies formed much earlier than expected, it suggests that dark matter may have played a more significant role in their formation than previously thought. While the multiverse theory offers one potential explanation for these findings, other theories also offer potential insights. Regardless of which theory proves correct, these findings have significant implications for our understanding of the universe and the nature of reality itself. As we continue to study the universe and its mysteries, we may uncover even more profound insights into the nature of the cosmos and our place within it. The James Webb Space Telescope from NASA has recently provided insights into the early years of the universe which were previously beyond our reach. Specifically, a proto-cluster of 7 galaxies has been observed for the first time at a distance that astronomers refer to as redshift 7.9 or 650 million years after the Big Bang. The astronomers have used the data collected to predict the future development of this nascent cluster, finding that it likely grew to resemble the Coma cluster, a massive collection of galaxies in the modern universe. The lead author of the study, Takahiro Morishita, stated that the site of accelerated galaxy evolution observed is unique, and Webb has given astronomers an unprecedented ability to measure the velocities of the 7 galaxies and confirm that they are bound together in a proto-cluster. The precise measurements captured by Webb's near-infrared spectrograph were crucial to confirming the galaxy's collective distance and the high velocities at which they are moving within a halo of dark matter over 2 million miles per hour. The data allowed astronomers to model and map the future development of the group of galaxies all the way to our time in the modern universe. The prediction that the proto-cluster will eventually resemble the Coma cluster suggests that it could be among the densest known galaxy collections with thousands of members. Galaxy clusters are the most massive concentrations of matter in the universe, and they can significantly bend space-time. This bending, called gravitational lensing, can magnify objects beyond the cluster, enabling astronomers to see through it like a giant magnifying glass. By using this effect, the research team was able to view the proto-cluster by looking through Pandora's cluster. Even with Webb's powerful instruments, they still needed assistance from nature to see so far. Until the development of Webb's infrared instruments, it has been challenging to explore how large clusters like Pandora and Coma first came together due to the expansion of the universe stretching light beyond visible wavelengths into the infrared, where astronomers lacked high-resolution data. Webb's infrared instruments were designed specifically to fill in these gaps at the beginning of the universe's story. The view of a protocluster of 7 galaxies confirmed by Webb were initially identified as candidates for observation using data from the Hubble Space Telescope's Frontier Fields program. Webb picked up the investigation, gathering detailed spectroscopic data in addition to imagery and focusing on the galaxies scouted by Hubble. At a mere 3% of the universe's current age, or 350 million years, objects have been discovered that are much larger than what was previously believed possible for galaxies that formed so soon after the Big Bang. If these findings are confirmed, they will challenge the current understanding of how the earliest galaxies came into existence. Joel Leja, co-author of the study and an assistant professor of astronomy and astrophysics at Penn State University, stated that these objects are much more massive than anticipated. The expectation was to find small, young galaxies at this stage, but instead, galaxies with a similar level of maturity to our own have been found in what was thought to be the earliest era of the universe. The discovery of incredibly massive galaxies close to the beginning of time has left scientists questioning their understanding of the early universe. Current models suggest that after a rapid expansion, the universe cooled down enough for gas to collapse into the first stars and galaxies during a period known as the Dark Ages. However, the recent discovery of such massive galaxies challenges this understanding, suggesting that the universe may have been filled with star formation far earlier than previously believed. This finding could require a revisiting of the basic principles of cosmology or a rethinking of how the first galaxies started from clouds of stars and gas, specifically the formation and assembly of galaxies. The study of the universe has been a fundamental part of human inquiry for centuries, and with each passing year we uncover new mysteries and challenges to our understanding of the cosmos. One of the most fascinating aspects of this inquiry is the possibility that there are multiple types of universes, each with its own unique properties and characteristics. One of the most widely accepted models of the universe is the Big Bang theory, which posits that the universe began as a singular point of infinite density and temperature and has been expanding outward ever since. While this theory has been the subject of much scrutiny and debate, it remains one of the most important and widely accepted models of the universe. Another model of the universe is the inflationary universe theory, which builds on the Big Bang theory by suggesting that the universe underwent a period of rapid expansion in the first fraction of a second after the Big Bang. This theory offers a possible explanation for why the universe appears to be homogeneous and isotropic on a large scale. The collapsing universe theory, on the other hand, suggests that the universe will eventually collapse in on itself due to the force of gravity, leading to the eventual end of the universe in a big crunch. This theory offers a different perspective on the eventual fate of the universe and raises important questions about the ultimate destiny of our cosmos. The multiverse theory suggests that our universe is just one of many universes, each with its own unique set of physical laws and properties. This theory offers a radical departure from traditional views of the universe and invites us to consider the possibility of alternative realities beyond our own. Finally, the theory that we are living in a simulated universe suggests that our reality is not entirely real, but rather a computer simulation created by a highly advanced civilization. While this theory may seem far-fetched, it raises important questions about the nature of reality and the role of technology in shaping our understanding of the universe. Taken together, these different models of the universe offer a diverse range of perspectives on the nature of reality and our place within it. While some of these theories are more widely accepted than others, each offers its own unique insights and challenges to our understanding of the cosmos. As we continue to explore the universe and uncover new mysteries, we may find ourselves drawn to one or more of these theories as a way of understanding the profound questions of existence and meaning that have captivated us for centuries. The multiverse theory is a speculative idea that suggests that there may be many different universes beyond our own. It is based on the notion that the universe we observe may be just one of many, each with its own set of physical laws and constants. The idea of multiple universes is not a new one, and it has been discussed by scientists and philosophers for centuries. However, the concept gained renewed interest in the 20th century with the development of quantum mechanics and string theory. In quantum mechanics, particles exist in a state of superposition, meaning they exist in all possible states simultaneously until they are observed, at which point they collapse into a single state. This has led some physicists to suggest that there may be many different universes, each representing one possible state of a quantum system. String theory, which attempts to unify the laws of physics, also suggests the existence of multiple universes. According to string theory, the universe is made up of tiny strings of energy vibrating at different frequencies. These vibrations correspond to different particles and forces in the universe. However, string theory requires the existence of more than 3 spatial dimensions, which means that the universe may have many more dimensions than we observe. Some physicists suggest that these extra dimensions may be curled up into tiny spaces, creating many different universes. There are several different types of multiverse theories, each with its own set of assumptions and implications. One type of multiverse theory is the many worlds interpretation of quantum mechanics. According to this theory, every possible outcome of a quantum measurement exists in a separate universe. For example, if a quantum system could be in 2 different states, both states would exist in separate universes. This would mean that there are an infinite number of universes, each representing a different possible outcome. Another type of multiverse theory is the bubble universe theory. According to this theory, our universe is just one of many bubbles in a larger space. These bubbles could be created by cosmic inflation, a period of rapid expansion that occurred shortly after the Big Bang. If our universe is just one bubble, there could be many other bubbles beyond our own, each with its own set of physical laws and constants. Finally, the landscape multiverse theory suggests that there may be many different universes, each with its own set of physical laws and constants within a larger landscape of possibilities. According to this theory, the laws of physics and constants we observe in our universe are just one possible set of parameters within a larger space of possibilities. While the multiverse theory remains controversial among scientists, it has gained popularity in recent years, particularly among physicists and cosmologists. Some researchers suggest that the existence of multiple universes could explain certain mysteries of the universe, such as the fine-tuning of physical constants and the apparent dark energy driving the expansion of the universe. However, the multiverse theory also raises many philosophical questions, such as the nature of reality and the limits of scientific inquiry. If there are multiple universes beyond our own, it raises questions about the nature of the universe and whether it is a single entity or a collection of many different entities. The multiverse theory is a speculative idea. While the theory remains controversial, it has important implications for our understanding of the universe and our place within it. As scientists continue to explore the mysteries of the universe, they may uncover more evidence for or against the existence of multiple universes, and the philosophical questions raised by the theory will continue to challenge our understanding of the nature of reality. The cyclical universe is a speculative idea in cosmology that suggests that the universe goes through an infinite series of cycles in which it expands and then contracts, leading to a never-ending sequence of big bangs and big crunches. This idea contrasts with the prevailing model of the universe, the Big Bang theory, which suggests that the universe had a single beginning and has been expanding ever since. The idea of a cyclical universe has been around for centuries, with some ancient cosmologies suggesting that the universe goes through a repetitive cycle of birth, growth, and death. However, the concept gained renewed interest in the 20th century with the development of modern cosmology and the discovery of cosmic microwave background radiation, which is seen as evidence for the Big Bang theory. One of the most famous proponents of the cyclical universe theory was the physicist and mathematician Albert Einstein. In the 1930s, Einstein worked on a theory of gravity called the cyclic model, which suggested that the universe could go through a cycle of expansion and contraction, with the expansion driven by dark energy and the contraction by dark matter. However, Einstein's theory was later abandoned due to its inability to explain certain observations of the universe. More recently, the cyclical universe theory has been revived by some theoretical physicists, who suggest that the universe may go through a never-ending cycle of expansion and contraction. One version of this theory, called the ekpyrotic universe, suggests that the universe was created from a collision between two higher dimensional branes, or membranes, which caused a big bang and a subsequent expansion. After a period of expansion, the universe would contract back to a single point, leading to another collision and another cycle of expansion and contraction. Another version of the cyclical universe theory, called the conformal cyclic cosmology, was proposed by the physicist Roger Penrose. This theory suggests that the universe is infinite in age and goes through a never-ending cycle of eons, each consisting of an expansion phase followed by a contraction phase. According to Penrose, the universe is self-similar, meaning that each eon is like the previous one, but with a slightly different physical state. While the cyclical universe theory remains controversial among scientists, it has important implications for our understanding of the universe and its fate. If the universe is indeed cyclical, it suggests that there may be no ultimate beginning or end to the universe, and that the laws of physics and constants may be able to survive each cycle. It also raises questions about the fate of life and intelligence in the universe, and whether they could survive each cycle. However, the cyclical universe theory also raises many questions and challenges for scientists. For example, it is unclear what mechanism could drive the contraction phase of each cycle, and whether it would be strong enough to overcome the expansion driven by dark energy. It is also unclear how the universe could maintain its physical laws and constants through each cycle, and whether there would be any observable differences between each cycle. As scientists continue to explore the mysteries of the universe, they may uncover more evidence for or against the existence of a cyclical universe, and the challenges and questions raised by the theory will continue to challenge our understanding of the nature of the universe. The simulation hypothesis is a speculative theory that suggests that the universe, including our own existence, is a computer simulation created by an advanced civilization. The basic idea is that our reality is not actually real, but rather a digital construct, much like a video game or virtual reality simulation. The idea of a simulated universe has been around for centuries, but it gained renewed attention in the 21st century, thanks in part to advancements in computer technology and the popularity of science fiction. The theory is often associated with the philosopher Nick Bostrom, who outlined the argument in a 2003 paper titled, "Are You Living in a Computer Simulation?" The basic argument for the simulation hypothesis goes like this: if it is possible for a civilization to create a computer simulation of reality, and if such simulations are likely to be created by advanced civilizations, then it is more likely than not that we are currently living inside a simulation. Bostrom calls this the simulation argument. One of the main reasons why the simulation hypothesis is taken seriously by some scientists and philosophers is that it is difficult to disprove. If our reality is indeed a simulation, then there would be no way for us to know it for sure, since the simulation would be designed to be indistinguishable from reality. This is known as the simulation constraint. Another argument in favor of the simulation hypothesis is that it would explain certain features of our universe that are difficult to explain otherwise. For example, some physicists have pointed out that the universe seems to operate according to mathematical laws and principles, which could be seen as evidence that it is a simulation created by a computer program. However, there are also many criticisms of the simulation hypothesis, and it remains a controversial idea in the scientific community. One of the main criticisms is that there is no direct evidence to support the theory, and that it relies on unproven assumptions about the capabilities and motivations of advanced civilizations. Others argue that the simulation hypothesis is not a scientifically testable hypothesis, since it is impossible to gather empirical evidence to support or refute it. Despite these criticisms, the simulation hypothesis remains a fascinating and thought-provoking idea, and it has captured the imagination of many scientists, philosophers, and science fiction fans. As our understanding of computer technology and the nature of reality continues to evolve, it is possible that we may uncover new evidence or develop new theories that shed light on the ultimate nature of our existence. Until then, the simulation hypothesis will remain one of the most intriguing and controversial ideas in science and philosophy. The topics covered in this conversation represent a diverse range of theories and concepts, from the cutting-edge science of astrophysics to the esoteric theories of consciousness and the nature of reality. Despite the apparent differences between these topics, they are united by a common thread: the human desire to understand the world around us and to seek deeper meaning and purpose in our lives. The James Webb Telescope's discovery of distant galaxies challenges our current understanding of the universe and invites us to consider the possibility of alternative models of reality, such as the cyclical universe theory or the multiverse theory. While these theories are still largely speculative, they encourage us to expand our imagination and to question our assumptions about the nature of reality. Similarly, the theory that we are living inside a simulation challenges our understanding of consciousness and the boundaries between the physical and the virtual worlds. While this theory may seem far-fetched to some, it raises important questions about the nature of reality and the role of technology in shaping our experience of the world. These diverse topics remind us of the power of human curiosity and imagination and of our innate drive to understand and connect with the world around us. Whether we are looking to the far reaches of the universe or exploring the inner landscape of our own consciousness, we are continually seeking to expand our horizons and to deepen our understanding of the mysteries of existence. In many ways, these theories and concepts represent the ongoing evolution of human thought and the search for deeper truths about ourselves and the universe. While some of these theories may be more grounded in science or spirituality than others, they all offer unique perspectives on the nature of reality and the potential for human transformation and growth. Ultimately, whether we are exploring the far reaches of the cosmos or the depths of our own consciousness, the journey of discovery is a never-ending one, full of mystery, wonder, and endless possibility.